Hi, in this video, we're going to take a very brief look at generalized linear models. All right, so the big idea of generalized linear models is that I want to do linear regression, but I don't have the right probability distribution going on. All right, so remember when we talk about linear regression, we make the assumption that our residuals are normally distributed with zero mean, constant variance. Okay, well, let's say we look at our data and it's very clear that normality doesn't apply. So let's say that I've got, two levels of data. Let's say success, failure, broken, not broken. We could have, history of, you know, criminal conviction or no criminal convictions, two levels. And we can represent that with zeros and ones. All right, well, that's Bernoulli. That's a binomial on there. That's nowhere near Gaussian normal distribution. Or maybe I have counts, maybe the number of collisions at an intersection. Or maybe there's other possibilities for the Poisson, or maybe we look at it and we think, hey, maybe I've got a negative binomial from the number of counts. All right, so when I'm in these situations, linear regression can provide a model because I do have count values, but it doesn't really work right. I don't have the right mathematical structure. What generalized linear models do is that these expand linear regression to handle other types of probability distributions. And so GLMs are flexible statistical models that allow for the response variables to have error distribution models other than Gaussian. This is a generalization of linear regression by allowing the linear model to be related to the response variable via a link function, and by allowing the magnitude of the variance for each measurement to be a function of its predicted value. All right, so now we're making things more flexible. There are three components to a GLM. We've got the random component, the systematic component, and then we have the link function. The random component is the probability distribution aspect. And so when we're doing GLMs, the distribution needs to be what's called an exponential family of distributions. All right, so that's just a class of probability distributions that have a lot of very nice mathematical properties. And so examples of these are normal, binomial, Poisson, gamma, and inverse Gaussian. Okay. Now the systematic component, this is the combination of our coefficients and our predictor variables. So our explanatory variables, the predictors, are combined linearly. So when I say linearly, that's the coefficients, coefficient multiplies predictor variable added up. This is similar to multiple linear regression, where the predictor variables are summed by the weights to give a predictive value. Now, the last part, and this is important, is the link function. The link function connects the expected value of our target variable to that systematic component. And so the link function provides a relationship between the random component, the probability distribution of the random variable, and the systematic component, that is our predictors. The link function transforms the expected value of the response variable to create a linear relationship with the predictors. So the link function enables us to connect the expected value of our target variable to all of our predictor variables and their coefficients. And so, for example, with logistic regression, which is a type of GLM, a logit link function is used to connect the probability of an event happening to the linear combination of predictors. Now, when I'm doing neural networks, the link function is the inverse of the activation function in neural network speak. So, if you hear activation function, the inverse is the link function. GLMs provide a broad framework that includes a special case of multiple linear regression, and when the response variable is normally distributed and the identity link is used. So when I'm doing regular old multiple linear regression, I'm actually doing a generalized linear model. Here, I'm assuming normal distribution, and I'm using the identity link. When I'm doing logistic regression, so that's when we have a binary target variable, and we're using the logit link. Poisson regression, this is when we have counts, and we use the log link on this one. And there's a bunch of other ones, so I can have a whole collection of distributions, a whole collection of link functions that work out depending on my problem. Estimation in GLMs is typically performed using maximum likelihood and involves finding the parameters that maximize the likelihood of the observed data given the model. GLMs are widely used in many fields where data analysis is required, including biology, medicine, social sciences, and engineering. I mean, GLMs are used basically everywhere that there are statistics. All right, so now let's talk about the random component in our generalized linear model. All right, so here, the random component refers to the probability distribution of the response variable. This distribution must be a member of an exponential family of distributions. An exponential family distribution is a set of distributions whose probability density function can be represented using this equation. All right, so notice that our target variable is y. I've got y here, and I've got y here. And it can work out that the c is a constant function or 0. And that's okay to work out. Here, y is our target variable. Theta is the natural parameter distribution. A of phi is the dispersion parameter. And b of theta and c are known functions. The function a can vary depending on the choice of distribution, but it's common for many distributions in the exponential family to have the identity function or squaring. Different choices of theta, a phi, b theta, and c, lead to different members of exponential families. For instance, if we take a equal to the identity function, b equal to negative log of negative theta, and c is equal to negative log of the factorial, we'll get the Poisson distribution with theta equal to log of lambda. And lambda is the rate parameter for our Poisson distribution. All right, so an important property of exponential families is that the expected value of y given theta is the derivative of b of theta. And if you go deeper into the theory of generalized linear models, that's an important feature. And so it works out the expected value of y given theta is equal to the first derivative of b, like that. And so this is useful because it allows us to relate the expected value of the response variable to the predictors via the link function in the GLM. All right, now let's talk about the systematic component. And so here we're interested in our predictor variables and our coefficients. So the systematic component of a generalized linear model is the part of the model where the explanatory variables or predictors are found. It is essentially the linear predictor, a linear combination of the predictors with a set of coefficients called parameters that need to be estimated. All right, so if x denotes our predictor variables, then we can use beta for the coefficients, and the systematic component of our generalized linear model is the right hand of this equation. And so here you'll notice I've got my coefficients times predictor variables. And here we're saying that the predictor variable for the constant is a constant of 1. And so using matrix notation, I can simplify this as a dot product. And here, T denotes the transpose, or the matrix multiplication. The purpose of the systematic component is to incorporate the predictors into the model. In a simple linear regression model, the systematic component is the model itself. However, in a GLM, the systematic component is linked to the response variable via the link function. So the link function is how we get that bridge between systematic component and random component. All right, so this allows for the response variable to have a non-normal distribution and for the mean of the response variable to have a nonlinear relationship with the predictors. So now this is kicking up the flexibility by a lot. All right, so now let's talk about that link function. The link function in a generalized linear model is a component that provides the connection between our predictors and the expected value of our response variable. The link function allows for nonlinear relationships between the expected value of the response variable and the predictors. We don't have that level of flexibility in regular linear regression. In mathematical terms, mu denotes the expected value of the response variable, and nu denotes the linear predictor. The link function then is that g of mu is equal to nu. And so realize I don't have an error term on here because I'm dealing with expected values. Now, g is a known function, which will be chosen according to the needs of the analysis, and it transforms the expected value of the response variable to create a linear relationship with those predictors. One property that is typically desirable in a link function is that it is a monotonic differentiable function, which ensures that the GLM will have a unique solution that can be found by an iterative method. Now, we don't have to be monotonic and differentiable, but we really want it to be. So if I don't have a good reason not to, I'm going to choose a link function that's monotonic and differentiable. Different GLMs use different link functions. For instance, logistic regression for binary variables, we have the logit link function, which is log of the ratio of the odds ratio, log of the odds. In this case, the inverse of the link function, which gives the expected value of the response, is just this function here, where I go 1 divided by 1 plus negative exponential of what I have up here, of my g of mu. Another common choice is the identity link function used in ordinary linear regression. And so here, g of mu is just mu. And so the expected value of the response is just the linear combination of the predictors. Choosing the appropriate link function is critical for the performance and interpretation of our GLM. The choice is typically made based on the nature of the response variable, the assumed distribution of the responses, and knowledge of what we're working on. All right, so now let's go back to exponential families. And so exponential families is a rich class of probability distributions that include almost all of the common distributions that we work with. There are infinitely many distributions, but the exponential families are the ones that have a lot of nice properties. So if I can, when I do my analysis, I greatly prefer an exponential family over another one that won't have all these nice properties. And so examples of these are normal distribution, exponential, binomial, Poisson, gamma, and Bernoulli distributions. But there are more. A probability distribution belongs to an exponential family if its density function or mass function can be written in this format, where y is our target variable for this. Y is the outcome of the random variable. Theta is the natural parameter. A of phi is a function known as the dispersion parameter. Frequently, this will be a constant. And b is a function of the natural parameter. And c is just another function. Each specific distribution in an exponential family can be obtained by specific appropriate forms for knowing if we know these functions and the parameter. For instance, the normal distribution is an exponential family where A is the identity function, and we use the variance is equal to phi. B is theta squared over 2. Theta is equal to the ratio of the mean and the variance. And then C is negative y squared divided by 2 phi. A key advantage of the exponential family of distributions is that they have convenient mathematical properties that make them tractable in many situations. So, for example, generalized linear models and Bayesian inference. A notable property of exponential family distributions is the existence of a sufficient statistic for the natural parameter, which can simplify our analysis by a lot. Another property of the exponential family distributions is that the expected value of y given theta is the derivative of b, which I mentioned earlier. All right, so now let's get into the aspect that most of the time we actually struggle with when we're actually on the job, and that is getting the code to work. What I'm going to do, I am going to basically just vomit out example code to show you ways to use different distributions and different links with our data. Every single time I'm going to use the empty cars data set, and so GLM behaves a lot like the LM function. I have my formula, I have my data set, but I also need to specify the family. Now the family, either I can use a string, so like for Gaussian, or I can use the family function. And inside the family function, if I choose, I can identify what the link function will be. And so here, this model is going to be standard linear regression. Now, over here, if I change, here I've got Gaussian again, but now I have a different link function. So this is not linear regression. And here we have inverse going on for our link. And so here we're using the Gaussian distribution. Now, if I have binary data, zeros and ones, yes, no's, broken, not broken, success, failure, that type of data, I can use logistic regression. For logistic regression, I'm going to use the binomial family. And if I choose, I can specify the link. I don't have to. The default is logit. The default in Gaussian is identity. The default in binomial is logit. The logit link function is very flexible. In most situations, it's the better one to use. Its level of flexibility, honestly, you know, if it's not the best choice, it's close to the best choice. Every time that I've looked, every time I've worked on it, and I've gotten to the point where I don't even try other link functions because I've done enough models where probit and other ones didn't work out too well. Now, a lot of fields, especially like economics, like probit for the link function. Do whatever your stakeholders want you to do. Just go along. My opinion is probit. It does have a little bit of additional interpretability aspects to it, but it doesn't, when I've worked with it, it didn't fit as well as logit. I've only used it when my stakeholders specifically wanted to. Logit is flexible enough and interpretable enough, and that's by far the most well understood. So use a link of logit, which is the default. If you don't have a good reason otherwise, a second choice would be probit. And then we have others that we can also use, like Coshit. And then we have C log log. Now here, I couldn't get log to work, even though it's listed as a possibility. Now and now something that'll happen, if I'm overfitting, I can get predicted probabilities of zeros and ones. And when that happens, when my model is fitting perfectly, there's probably something wonky going on. When you see these warnings, this means that you're probably overfitting, or maybe you have variable leakage. Variable leakage. Variable leakage is where using a variable that you would not actually have for prediction at the time of prediction to make a prediction on. Now for gamma, here we can use the gamma distribution for time. And we have three choices of inverse, identity, and log. For Poisson, this is probably the third most common. I would say gamma would be fourth. Poisson, we have a link of log, we have a link of identity, and we have a link of square root. And we can change these links when we have dispersion aspects. So remember, with the Poisson distribution, the expected value and the variance are equal to each other. If it looks like the variance is greater than the expected value, when I look at my sample expected value, my sample average, my sample variance, then I can change the link to adjust. Now, inverse Gaussian. Here, I'm just using the family of inverse Gaussian, and we have different links here. You notice I have 1 over mu squared. And then the quasi, this is one that will handle data on 0, 1. And so like here, you notice I'm converting everything to zeros and ones. And we have 2 parameters for this. We have link and we have variance. And so, we can choose what's going on. I chose constant every single time. The quasi family, if you go around like, tinkering with things, it can be hard to get this to actually run. You need to specify your starting values frequently with this. So you'll notice that here I have to specify my starting values. So one thing that I found that's good practice for this, if I had to use the quasi family, which I have a few times, I had trouble getting things to go like this. I did regular logistic regression with the same link, got those coefficients, and put those coefficients in for the starting values. Now, after I get my model, I can use the summary function to take a look and evaluate what's going on. I can look at, my hypothesis testing. So here, this is that logistic regression model. And so here, there's, I would definitely want to reevaluate this model. This model is crap. I'm just showing it for demonstration purposes. We can get the effects from our GLM by using the effects function for ANOVA. Now, ANOVA doesn't work on all of the models. It doesn't work on, it doesn't do anything for logistic regression, but it does spit out some values that I can potentially use that would be on a, like the degrees of freedom. I can grab that. Here we have the deviance, if I want to use that. And the deviance connects to the chi-square distribution. I personally don't really bother with this. We can get the influence of different aspects of our model. So here's the influence for each row of data. Here are the coefficients, the influence of the row of data and its influence on the predictor coefficient. Sigma for our variance estimate. Here is the weight of the residuals. We can extract the fitted values. We can grab the residuals, and we can make a prediction using new data. If I run predict without new data, it will grab the fitted values. If I want to get the, if I want to predict on a new data set, I have to put comma, new data equals whatever data I need. And we also use plots. And so there's going to be 6 plots, just like with linear regression. Now, the plots are a little bit harder to interpret. Notice I have a curvature because I've got 2 levels on this. It's a logistic regression. Here's my normal QQ. All right, so that looks like it's not normally distributed, but I'm in logistic regression. That's not, that's not a problem. Here's the scale location plot. Here's Cook's distance. Now remember that in R, base R will always mark the most 3 extreme ones. And so here I definitely would want to check, does the Volvo 142E, does it belong in my data set? Is there an error in there? Why is it sticking up so much more than all of the others? And here's my residuals versus leverage. And we notice the same 3 come up again. So these are ones that I would want to check out, especially this Volvo. Here is the Cook's distance versus leverage. And so it's flagging 3. And so every one of these plots, it's labeling the 3 most extreme ones. And it can be different rows on different plots. Here's here's the Camaro and Merck 240D. And so these are all ones that I would want to just take another look at. All right, so let's wrap this up. My generalized linear model has 3 components: the random component, that is the probability distribution; the systematic component, that is a mixture of coefficients and predictor variables; and the link function that connects our systematic component to the expected value of the random component. We need to choose our distribution and link function based off of our data and the nature of our analysis. And we want to, check the validity of our model after we build it, of course. And GLMs are used all over the place. Every time you see Poisson regression, every time you see logistic regression, you're seeing a generalized linear model. All right, well, that's all I've got for you. Life is short. Do math.